Okay, cool. My name is Megan Zori. I'm a software engineer with Epic Solutions. I'm going to be doing this first lightning talk, which is going to be about synchronizing radio time. So, in a lot of SDR applications, kind of a common workflow is you receive a bunch of data, you do some decoding of that data, and you detect some event that occurred at some sample offset event. One of the biggest problems is you don't really know what that number n actually means as far as real world time. So, when did you actually detect that event as far as the wall clock? So what we really need is a way to correlate samples and radio time or sample time with an actual wall clock time. There are a lot of different applications that require this, including MIMO applications, TDOA applications, and really any sort of application where you want to synchronize your control of the system. One of the most common ways to achieve this synchronization is to use a 1 PPS source, which stands for 1 pulse per second. There are a handful of different things that can generate a 1 PPS, with the most common being a GPS receiver. So a little bit more details about what a 1 PPS is. It's essentially this pulse that happens on a rising edge once a second. It's a fairly precise signal. It's typically on order of tens to hundreds of nanoseconds. One of our radios, our GPS receiver that we use at Epic, has a plus or minus 15 nanosecond accuracy. That radio happens to be our Sidekick Stretch product. We announced our Sidekick Stretch July of this year. So what that is, you can see it kind of pictured right in the middle of the screen there. It's a M2 22 by 80 standard form factor. What's useful about it, it has an integrated onboard GPS. It also has a handful of RX pre-select filters, so it lets you really refine what you're receiving. And the key component there is that it uses the analog device's 809361 RF chip. In addition to that, we also have our Thunderkick, which is essentially just a housed Sidekick Stretch product. And it interfaces with a host laptop through a Thunderbolt 3 cable. Digging a bit deeper into the Sidekick Stretch product, you can see a detailed block diagram up here. And one of the things that we have that kind of makes it real handy for the synchronization is a GPS discipline oscillator, which you see kind of towards the middle of the screen, a little bit lower. We also have a FPGA on board and kind of all the standard bells and whistles that you would come to expect with a SDR system, including accelerometer, temp sensor, FPGA for custom block processing. So here you can see a picture that I set up at our lab, and it's got a few things going on here. One of the things is right in the middle of the screen towards the bottom, we have our Thunderkick radio, and it is connected to the laptop through a Thunderbolt 3 cable. And on the laptop itself, we actually have GPS-D and GPS-MON, which is getting its GPS NEMA stream from the Thunderkick across the Thunderbolt 3 cable. We also have a Sidekick GNU radio flow graph going, and you can see that we're basically just plotting the time domain and frequency domain of the samples. Again, that's all coming across the Thunderbolt 3 interface. And then to realize the synchronization, one of the things that we added was a trigger source. So we added this trigger source to basically not start streaming data until we get a 1 PPS pulse. So what happens here is you start running your flow graph, and you set up the trigger source for 1 PPS, and you tell it go, and that very first sample that you receive from the radio directly correlates to the 1 PPS. Additionally, we're actually resetting our sample timestamp, so you'll see that the very first data has a timestamp of 0, and that correlates to a 1 PPS pulse. And I think I'm mostly out of time here, so if you want to hear more about the radios or anything else that Epic has to offer, you can come check us out at the expo. And if you want to check out our GitHub page for our Sidekick support, it's up. The link is up there.
Thank you very much, Megan.
Thank you.
You nailed the timing.
All right, so I'm Tom Rondeau from DARPA. So quick question, anybody here a professor? Really, only a few professors. Okay, maybe this was a mistake. Anybody here students? Cool, all right, so go back and tell your professors. So DARPA runs a program called the Young Faculty Award. If you're familiar more from the academic world with the NSF Career Award, this is kind of like our version of the Career Award. I think it's $250,000 a year to a young faculty. There's definition of what a young faculty means. Course level, it's like the first 8 years of your tenure track position you kind of count with some caveats. You have to be at a US institution, not a US citizen. But so we just released the 2020 research announcement for the YFA about a week ago. I think abstracts are due soon, within the next week or so. You don't have to submit an abstract to do this, but it's a great opportunity to take a look at a whole bunch of, a whole bunch of topics. So there are tons of topics that we post as part of the YFA announcement, and you're going to submit against one of these specific topics here. The reason why I decided to come up here and broadcast this publicly is because of one topic in particular that I put out there, which is this physics-based re-exploration of spectrum allocation. So at a high level, this asks the question, if we didn't have 100 years worth of spectrum policy behind us that codifies some ways that we interact with the spectrum based on when they thought HF was really actually high frequency, we know a lot more about the physics. We have a lot more technology that accesses that spectrum, a lot more signal processing and mathematical knowledge of this. How would you rethink the way that we allocate spectrum based on all that we know and all that we can access? So I'm asking people to make sure that they are rooted in spectrum policy, that they know where all this comes from. They understand the technology, they can run experiments for RF propagation and analysis, and then come up with some ideas for what would a kind of tabula rasa of spectrum policy look like if we went into the future without all this encumbering background. So it's a big opportunity, I think, for young faculty to really become the next leader in spectrum regulations, the dynamic spectrum access world that I've been involved in. All of that, this is really trying to open that up to some new voices or some young faculty that can really kind of take hold of this and hopefully change things for how we think about it. And I will also say, I know we're mostly engineers in this room. This question is bigger than engineering. It's social, it's political, it's economic. So economists, business professors, we want to make sure that it's multidisciplinary and can pull in together a team of folks that can look over this entire spectrum of RF spectrum. All right, thanks.
Thank you very much, Tom.
Hi, my name's EJ Kreiner. I work with Hawkeye 360. I'll give a talk later on some of that work, but right now I want to go through one of the projects that I put together as over the past year as a bit of a side project, and this is called Theseus cores, and so the idea here is that we want to provide open source FPGA cores for digital signal processing and software-defined radio. And then we'll throw in the batteries included. So I'll tell you what that means. Okay, the problem that I would like to solve here, to some extent, is that I can't find open source answers to important DSP problems for FPGA code, and I would really like to find that, but I couldn't. So I'd like to build that. You know, things like how to channelize spectrum, how to change the sample rates, modulate data, demodulate data, recover timing, all sorts of fun questions that have been solved for decades, literally decades, but there's still not reliable open source code for it. I think this is really important going forward. In the next couple of years, we'll have Xilinx's RF SOC, where you've got 1 to 2 giga samples of direct sampling. And what are you going to do with all of that? I think part of the answer could be use the FPGA for that. So the goal with this project is to provide open source DSP utilities. They're FPGA first, so they're not tied to any particular infrastructure. That said, the batteries included pretty much boils down to RF NOC integration right now, because there are platforms that support RF NOC, and if you can just build a bit stream and put it on hardware that's there with these cores and get up and running, then I would consider that a very meaningful success. Oh, quick aside, Theseus is referring to Claude Shannon's maze-solving mouse named Theseus. So we all know Claude Shannon here, of course, invented Boolean computing and information theory. Quickly go over some nuts and bolts. So the way I've set this up is, and I'll also talk about what it provides right now. But I've set this up as what you might call a mono repo, I suppose. So the core of it should be FPGA standalone code. So it's not tied to any infrastructure, but it does something like provide a polyphase channelizer. Then there's FPGA wrapped by RF NOC. We could also iterate on this and add other things like FPGA libIO or FPGA MathWorks, whatever your tool of choice would be. We provide a UHD-based out-of-tree module to interact with RF NOC and provide the software hooks. Also have a GNU Radio out-of-tree module, so you can put this in your GNU Radio prefix and compile and have blocks that show up in GNU Radio. On top of that, there's also a Theseus Docker repo that does some images, and I pulled this image yesterday. I've set up images to build on the master branches of UHD and GNU Radio for the last 6 months so that we can pull these down and build the software, hopefully, in a continuous integration. Basically, my idea here is that all FPGA code I've seen open source online just breaks pretty much as soon as it's put up. So if we can avoid that, I'd be very happy. Let's make sure it doesn't break magically. What does it do right now? There's 3 cores that we support. 2 of them are really simple hack-together versions of RF NOC code, but still helpful. So one is a DDC block that you can parameterize the number of DDC channels. It's basically Edis's DDC copied in a for generate loop, and you can add multiples of them. But it's actually pretty nice to have that as a channelizer in some cases. There's also, I needed a rational resampler to run on the N310 because it has kind of weird sample rates, and if I want something exactly at 2 megahertz, well, you have to resample it. So brute force channelizer right now, interpolate, decimate, done. There's a lot of room for this to be better. The third one, Phil Valence has put in a ton of effort to get the polyphase channelizer, polyphase filter bank channelizer working at FPGA. This is the standalone FPGA code. Michelle told me this morning, it's great, it works. so that's pretty good. But overall, this is still under development. It's very much a developer tool right now, like a lot of GNU Radio and RF NOC stuff. So you kind of have to have some expertise to be able to wrangle it. But it's somewhat unstable, and there's not very much in it. But that said, I'm happy to keep going with this and see where it goes and add more code. And I'd like to bring more people in who are interested in doing FPGA work in their spare time. All of you out there that want to do that. So another thing I'm considering here is doing a Friday workshop with Theseus cores. So I kind of wanted to take the time to just poll the audience and see if people would be interested in that and who would kind of be interested in having that discussion. Okay, a lot. All right, good. Okay, yeah, so I'll do it then. We'll do a Friday Theseus cores talk.
How many people actually raise their hands?
There's probably 10 or so, 10,
okay.
15.
If it's enough, you should talk to Michelle maybe about getting one of the breakout rooms.
Okay.
So you have space. Okay.
Yeah, great. Thank you.
All right.
Hi everyone, I'm Paul Sutton from Software Radio Systems. Just want to tell you a little bit about SRSLT, our open source project, for those of you that don't already know it. So if you've heard of SRS, you've probably heard of us because of SRSLT. Open source, full stack applications for the UE, the eNode B, and the EPC, the end-to-end network. GitHub, github.com/SRSLT. Everything's there in the one repo. We've got Launchpad PPAs for Ubuntu. Link is at the bottom there. Fairly active community, mailing list, again the link is at the bottom. A fair bit of activity going on. People saying nice things about us on Twitter. A lot of researchers using our software. I think we've got 100 publications listed on the srslt.com website at the moment. Some really interesting work going on. And again, a huge amount of traction within the mobile security domains. A lot of people using our tools for mobile security testing. We have a full UE application with hard SIM support. So really interesting tool for fuzz testing and general mobile security testing. You've probably seen some of the stories around users of SRS-LTE. This one was one where presidential alerts could be spoofed. That was using SRS eNode B, a group from Colorado. Again, focusing on the mobile security side of things, GSMA has this Mobile Security Hall of Fame. These are all the most recent coordinated vulnerability disclosures. These are the ones that were using SRS-LTE. So if you have any interest in talking LTE, talking open source, talking SDR, then come and find me. Some of the other interesting things we've been working on, obviously a lot of 5G development. If you're looking at our repos, you'll see some of the 5G NR stuff going in there. We've been doing a lot of work on FPGA support, so we're doing a lot of porting to Zynq UltraScale Plus platforms. We've been doing a lot of work in the air-to-ground space. Again, look with the Zynq platform, we've got a CubeSat in orbit at the moment. We've got a modified UE running on the CubeSat with a ground station in Texas talking to that. So quite a lot going on. I'm more than happy to talk one-to-one on any of those topics. Thanks very much.